Hey YouTube, what's up? Dr. T here. So, how about taking a little trip into one of my favorite areas? And here, a publication, a brief survey of deep reinforcement learning, which I'm going to read through along with taking some video clips of a seminar on the same subject by none other than our own Pieter Abbeel, esteemed lecturer of the CS 188 Introduction to Artificial Intelligence, available on YouTube from Berkeley. So, first of all, let's go and read a few pages, and I'll set my timer, and then we'll come back for a little bit of his introduction to his lecture. I'm not going to go through the abstract. I'm just going to start with introduction and move along a bit. One of the primary goals of the field of artificial intelligence, AI, is to produce fully autonomous agents that interact with their environment to learn optimal behaviors, improving over time through trial and error. Crafting AI systems that are responsive and can effectively learn has been a long-standing challenge, ranging from robots, which can sense and react to the world around them, to purely software-based agents, which can interact with natural language and media. A principled mathematical framework for experience-driven autonomous learning is reinforcement learning. The subject matter I'm currently learning and working my way through my own very grid world code. Although RL had some successes in the past, previous approaches lacked scalability and were inherently limited to fairly low dimensional problems. These limitations exist because RL algorithms share the same complexity issues of other algorithms, namely memory complexity, computational complexity, and in the case of machine learning algorithms, simply complexity. What we have witnessed in recent years, the rise of deep learning, relying on the powerful functional approximation and representation learning properties of deep neural networks, has provided us with new tools to overcome these problems. The advent of deep learning has had a significant impact on many areas of machine learning, dramatically improving the state of the art in tasks such as object detection, speech recognition, and language translation. The most important property of deep learning is that deep neural networks can automatically find compact, low-dimensional representations, namely features, of high-dimensional data. For example, images, text, and audio. Through crafting inductive biases into neural network architectures, particularly that of hierarchical representations, machine learning practitioners have made effective progress in addressing the curse of dimensionality. Deep learning has similarly accelerated progress in reinforcement learning with the use of deep learning algorithms within reinforcement learning, defining the field of deep reinforcement learning. And my interest in this is because I'm just about to step out of Q learning into deep reinforcement learning. So this is an interesting subject to kind of take a look at. The aim of this survey is to cover both seminal and recent developments in deep reinforcement learning, conveying the innovative ways in which neural networks can be used to bring us closer together, developing autonomous agents. For a more comprehensive survey of the recent efforts in deep reinforcement learning, we will be moving right along. Deep learning enables reinforcement learning to scale to decision-making problems that were previously intractable, i.e., settings with high-dimensional state and action spaces. Amongst recent work in the field of deep reinforcement learning, there have been two outstanding success stories. The first, kickstarting the revolution in DRL, was the development of an algorithm that could learn to play a range of Atari 2600 video games at a superhuman level directly from pixels, which we know is the seminal publication in Nature by DeepMind, which got the attention of Google, which said, we want them, buy them, and they did. Providing solutions for the instability of function approximation techniques in reinforcement learning. Well, where am I? Go on a little bit more. This work was the first to convincingly demonstrate that reinforcement learning agents could be trained on raw high-dimensional observations solely based on a reward signal. The second outstanding success was the development of the hybrid deep reinforcement learning AlphaGo. Once again, DeepMind. They've had an amazing impact on this field. AlphaGo, that defeated a world human champion in Go, paralleling the historic achievement of IBM's Deep Blue in chess 2 decades earlier. There's no comparison whatsoever between what Deep Blue did, which was a handcrafted set of algorithms put into a machine to play chess, and the current state here. But they're drawn upon as, whatever. And IBM's Watson's Deep QA system, another system that is heavily biased to specific kind of directives in terms of how it goes about understanding a complex question answer system based on lots and lots of data. Once again, that did not really involve deep reinforcement learning. That beat the human Jeopardy players. Unlike the handcrafted rules that have dominated chess playing systems, AlphaGo was composed of neural networks that were trained using supervised and reinforcement learning in combination with a traditional heuristic search algorithm. So I'll stop at this point. It's a good bit of an introduction, and we'll go over and listen to, if you're following me, a eminent professor of robotics teaches his 10 cents on deep reinforcement learning.
Welcome back. Our next speaker is Pieter Abbeel UC Berkeley, and we're looking forward to his talk on deep reinforcement learning.
Thank you. Good morning, everyone. So a lot of my work is in deep learning for robotics, and the kind of prompt for today was to make a talk about representations in deep reinforcement learning. So first time I'm giving this talk. Let's see how it goes. Let's start with some background. Reinforcement learning considers a setting where we have an agent, which is the thing we want to find a good program for. The agent gets to choose from a set of actions. After taking an action, the environment will change state, will emit a reward signal, and then the agent acts on the changed environment, and this cycle just repeats over and over and over. And so what makes this fundamentally different from something like supervised learning is that the supervision here is in terms of how much reward you accumulate over time, rather than supervision directly on which action you should be taking, in which case it would turn back into a pattern recognition problem. So What kind of problems can you model this way? Robotics, where a robot chooses an action, world changes, takes the next action, repeats. Dialogue, when you have extensive dialogue with people. Logistics, gameplay, and so forth. Anything where after you take an action, the world changes state, and you have to act in the changed environment that you caused yourself. Here are some recent success stories and some slightly older success stories. So top row, what do we see here? From Peter Stone's lab at UT Austin, the Robocop IBOs that learned with reinforcement learning how to control themselves to run faster than the other IBOs that they play against. Andrew Ng's group at Stanford, helicopter control. Russ Tedrick's work at MIT, control for a biped walker. And Jan Peters in Germany on swinging a ball into a cup. These are hard control problems, and learning enabled to solve these problems, and otherwise maybe it would not have been possible. These use somewhat traditional representations where you do heavy feature engineering, you represent everything in the control policy or whatever else you're trying to represent, we'll get to that soon, with a set of features you design, and then only a few parameters you tune. Recently, there's been a lot of progress where the representations being used are much more open-ended. They're deep nets. They can represent pretty much any function. And that has allowed people to have success in learn to control an agent that plays Atari games, continuous control in simulation, continuous control in the real world, and also to play the classical game of Go. And so what we'll see today is we'll see some of the algorithms behind this and the representations that go with them. So it turns out in reinforcement learning, there's not just one algorithm, and we can't just like say, oh, here's the algorithm, and now let's learn the representation for the thing that's sitting inside the algorithm. There's many, many approaches to solving the problem. Broadly speaking, there is policy optimization and dynamic programming. Policy optimization directly considers a control policy and tries to optimize it and gets the best performance on the task. Or tries to get the best performance on the task. Dynamic programming tries to decompose the problem over time into pieces and solve for a solution based on the temporal decomposition. Based on these different approaches, these different kind of fundamental approaches, there are different algorithms that emerge. The ones I'm going to look at today are policy gradients, actor-critic methods, and Q-learning. Actor-critic methods actually bring together both policy optimization and dynamic programming methods in.
Just to interrupt for a second, Q-learning. That's the elements of the technique that I've been studying and which I've been coding into my current grid world, which is almost complete. So that's the side of this little diagram that I'm on right now.
Into one. And Q-learning is just dynamic programming. OK, so this is the talk outline. I'll cover the algorithms, then we'll look at the representations that are underneath these algorithms. We'll look at some representations used for exploration, and then we'll also look at somewhat different algorithms that have emerged that have different representations underneath that don't exactly maybe fit the classical paradigm. And then at the end, we'll also look at algorithms that are yet completely different, that in some sense where you try to learn the algorithm completely rather than still designing the algorithm. And so that's a very different approach than the most successful ones so far. OK, so in policy optimization, we have this policy pi theta, which defines which action to take in a given state. It's parameterized by a vector theta. We want to find the best vector theta. So this could be a deep neural net with many free parameters. And the objective is to find the parameter vector that maximizes expected sum of rewards over time. Expected sum of rewards because often the environment is stochastic, and so you can't maximize deterministic rewards. You maximize what an expectation you're going to get. Often the policy itself is stochastic too. That can be a good thing. Even though very often you can show that the optimal policy would be deterministic, a stochastic policy can help you with smoothing out the optimization landscape. So you might start rather high entropy with your policy, and then over time, entropy will decrease, and that will help you find a better policy. OK, so one of the standard ways, maybe the most common way to compute a gradient for your policy is the likelihood ratio policy gradient method. And the beauty of this method is I actually don't need the dynamics model of the world, and that'll fall out in a little bit. So when we have a sequence of states S0, action U0, and so forth till last time capital H, we'll have rewards at each time step, and we'll summarize the whole thing with a trajectory variable tau, and we'll say, OK, we're trying to maximize utility as a function of our parameter vector theta that parameterizes the policy, which is expected reward associated with trajectories times, and this is then the probability of following that particular trajectory. So this is what we're trying to optimize for, and later we'll redecompose it into states and actions. Okay, let's take a look at what we can do here. We're trying to optimize this objective. We want a gradient to know in which direction to step. So this would be the gradient that we're trying to compute. Next step, we're going to bring the gradient inside the summation. Then we play a little trick that we can play in hindsight that might be a little puzzling right now, but it'll help us. We multiply and divide by the same thing, probability of a trajectory, put that in front of the gradient. Now what we can do is we can bring this underneath the gradient, and what we have here is the grad of the log probability of the trajectory. And so this is the expression we're going to work with. Why do we put it into this format? There's several reasons. The reason that we can already see right now is that we have an expectation now. This is an expectation, so we could sample and compute an empirical average of this expression. We can sample according to the current policy, which will effectively take care of this expectation up front. And this, we then have to compute along the trajectories to get our empirical estimate of the gradient. So that gives us this equation over here. So this is the likelihood ratio policy gradient.
So I'm going to stop at that point because I want to put about an equivalent amount of time in one side of this to the other. And let's just bring this back. And I'll see you next time, maybe.